This is my talk about strfry, a program I wrote. My name is Doug Hoyte. There's this protocol that was created, I think about 3 years ago, called Nostr, or some people call it Nostr, and it stands for notes and other stuff transmitted by relays, right? The idea behind it is to make like a really simple protocol that can be used to do like social media kind of things, like a Twitter or Reddit alternative. Extremely simple protocol. And I'm going to explain the entirety of it to you in the first few slides. But it's really just JSON messages that are cryptographically signed. And there's no like blockchains or cryptocurrency or anything like that in this. So it's just signed messages transmitted over WebSockets, right? They call servers relays, which is kind of like reminiscent of IRC, right? Internet relay chat. And what they are is WebSocket servers. And clients come and post their WebSocket messages to the relays. And then they also come and download them again from other relays. Typically, clients will post to many different relays, like in parallel for redundancy, right? In case of one ever goes away, you've got another relay that you've kind of backed it up on. So this is why I think Nostr is cool. It's why it's a neat design. First of all, you have this client sort of choice aspect to it. You can choose, web, mobile, desktop. There's many different, probably like 50 plus clients. So if you don't like one, it's easy to move to another one. And also your data is portable, right? So once it's uploaded, any client can access it, right? Like your contact list, if you move to another client, will just be there, right? Everything is like very compatible, and you can always back up your data and move it to other relays and things like that. And also, it's just it's a real community-driven thing. It's not under control of like any one particular company, right? And this is when, I haven't seen too many other protocols like in my career that I really feel are like this, like that are actually created by a community, right? Usually there's some company behind it pushing it or something, and there's like an official reference implementation, for example. But Nostr is not really like that, right? It's just this loose consensus of people building stuff. And, some things don't work properly. It's very chaotic, and but it's just a fun environment. And then I just wanted to compare it to Mastodon too, which a lot of people have heard about. I also like Mastodon. I think it's really cool, and hopefully succeeds as well. And I say it's spiritually similar, but I think Nostr excites me more, and this is why. With Mastodon, your identity is really just tied to one server, right? So there's been a lot of cases where that server just disappears, goes out of business, and you lose your contacts, you lose everything, right? Also, just the design of it is like the administrators of that server have a lot of like control over you, right? Like they can read your direct messages, right? So if someone DMs you, and whoever runs that server can read it, right? And also, they can control which servers they communicate with and so on. So it's really a difficult choice to pick which server you need to sign up for, right? Nostr doesn't have that issue, right? And I just want to notice that also Mastodon is actually a software implementation, not the protocol, right? So even the thing we talk about is the reference implementation for this thing, right? And if you want to build something that works on the actual protocol, activity pub, it's very likely not as compatible, right? Because you have to really follow what the reference implementation does. Okay, so I'm going to explain pretty much the entirety of the Nostr protocol to you here. Nostr is built of events, and what they are is JSON objects, and they have these fields. Okay, you have the ID, which is like the hash of all the other fields pretty much, and then the pub key, that's the public key of who is creating it. You have a creation timestamp, a kind, which is just an integer, and there's like, you can, different meanings for different kinds. And then there's a list of these tags, and then content is where you'd actually write your message, right? So that's just whatever arbitrary string you want to put in there. And then lastly, there's the signature of those fields, right? The public key signature, the signature using your private key. So when you want to post an event, you connect to a Relay's WebSocket and you send the event message, right? You just wrap it inside this little event array, first element of the event string, send it up to the Relay, and it records it. And if all goes well, it replies with this OK message, right? And there's also an error. You can put false if the Relay is rejecting it, and usually there's an error message as well. And then later on, when you want to download your events, you connect to a Relay, and then you pass it a rec message for request. And for that, you give it a subscription ID, because you can have multiple requests in flight at once. This is how it disambiguates it. And then you also have these filters, right, which are JSON objects that specify which events you want. Filters are quite simple as well. You pretty much just list what fields you want, and then if you give an array for each one, and any of those elements in the array, if any of them match, you should get the event, right? So if you wanted to get all of the events by those two pub keys, you would pass this as a filter, right? either that one or that one, right? However, when you have multiple different top-level elements inside there, it's an and match, right? So this last one, it needs to match that author and one of the kinds 0 or 3, and it needs to have been posted since this timestamp, right? So that's the filter. Responses are what the relay sends back to you. Remember we said that subscription ID to be A previously. That just gets associated with each event that's sent in response to the subscription, right? So responses are sent in 2 phases, right? First, there's all the events that were previously stored by the relay that exist in like its database. And then after that, it sends this end of stored events message. And then after that, it starts streaming in the second phase, this new events that come in real time, right? So you leave your WebSocket connection open and you get your new notifications and all this stuff in real time sent to you. And that's it. Like Nostr, there's these things called NIPs, Nostr implementation possibilities. And they're, kind of suggestions on how to use it, new things to change or whatever. But really what I just described to you is the full protocol. So you pretty much know enough to go implement your own client right now, for example, if you wanted to. So when you're building a relay, like that's the server component, the choice of the database is obviously very important, right? And depending on what path you start with will influence a lot of the different designs choices that you make later. Before I created strfry, almost all the relays were using SQL databases to do this, right? And the idea behind that is that you can take these filters, these JSON objects in that little language that I just explained, and translate them pretty simply into SQL, right? And then send to your SQL database, and it'll do a select for you, right? So that's quite convenient because it's very easy to iterate on that, right? You want to change your query slightly, you just change how the SQL is generated and so forth, right? And also most SQL databases are really good relational engines, and they have good query planners and good execution environments and things like that. So usually they're quite well tuned and tested well. So that's very nice. On the other hand, there's a lot of overhead for doing what we just described, right? First of all, you've got to create this SQL string. And if you notice, the SQL strings usually have to be fairly dynamic, right? Because you don't know how many kinds are going to come in that list, right? So, and how many different and tags you have to add on this and so forth, right? So usually you have to dynamically generate these SQL strings. And hopefully you're using prepared statements, of course, but then after you've generated it, you need to either send it to the DB or pass it into SQLite, for example. And then the engine needs to parse that SQL string, create a query plan, generate the little mini virtual machine and execute that, right? So there's a ton of overhead for doing SQL statements on this. And then secondly, you have limited control over the execution, right? When you send a SQL statement off to a server, it kind of just needs to run, and then you get the results back most of the time. There's not too many hooks on a SQL engine to actually be able to control some of the execution environment. So instead of SQL, what strfry uses is this database called LMDB. It's the Lightning Memory Mapped database engine. It's it was created for OpenLDAP originally, but it's a really, really flexible piece of software. It's an embedded key value database. Embedded means it's SQLite, for example. It just links into your program directly. And a key value, it means that it, of course, doesn't support SQL. It's just look up this key, get a value. It's what they call a single level store. It doesn't actually use any of its own buffering or caching or anything like that. It purely relies on the operating system's kernel, right, to use the file system cache as its memory cache, right? Which it has a lot of advantages that I'll explain. Underneath it works by memory mapping a file, right? And then you just want to read data from it. It's just there mapped into your memory. LNV has a bunch of benefits, or a bunch of things that make it pretty powerful. It supports ACID transactions. It's very, very durable. It's usually one of the best in terms of actually keeping your data safe. It doesn't really have too many knobs or anything you can tune with it, so it doesn't need too much maintenance or anything like that. In most cases, it just performs pretty well, except perhaps in lower memory conditions. But usually, it performs great. There's absolutely no locking in the read path, so you can have an unlimited number of threads, and they won't degrade each other, right? In the read path. There's no write-ahead logs or anything like that. When it crashes, if your program crashes, it can immediately start up again because it doesn't need to replay the logs or write-ahead logs or anything like that. And yeah, there's much less write amplification, which we'll talk about too, I think. So I said MVCC earlier. That stands for multi-version concurrency control. And the idea behind it is that you can have multiple different threads, accessing the database, and they don't necessarily all have the exact same view in the database, but they'll all have a consistent view that was basically a snapshot that was taken when the transaction started, right? I'll explain how that's implemented now. The idea behind it is this system called shadow paging, which is not a new concept. It's like it's been in databases since like the 80s. The idea is that you have a big tree. LMDB is a B-tree based design, and that's depicted by the white squares here. So when you want to look up a value, you start at the root page and you traverse down and you figure out where your value is, right? And that's where these little eyes are, right? They're like, just for example, transactions that are going and reading the database, right? So they're all seeing this white boxed tree, right? However, let's say a writer process comes in, it starts to create this little shadow page, right? And that'll be a modification. It'll be a new tree, right? But none of these transactions that are reading see anything about the shadow tree, right? They'll come in and then, start at the root page of the white tree and so on. And the shadow pages don't interfere at all, right? And any pages that need to get modified inside of the copy, the shadow version, are actually copied from the white boxes and created these new ones called green ones with the modifications, right? And then once the writer process is done, it commits its transaction, there's just an atomic swap, right? So this shadow page just atomically becomes the root page, right? So there's no locking required at all. It's kind of like an STD atomic exchange or whatever, right? LMDB is actually a C library. It doesn't use C++, but yeah, it's the same principle. And at this point, notice that we still have those reader processes, and they're still using the white boxed original tree, right? So this is where it can become a little bit confusing, is that you now have two versions of the database, right? You have this old version that was the original one, and that's what the previously existing transactions were still using, but now there's this new one. So if new transactions come in, they'll start to see this newly modified one. In this case, now it's been changed to the white box one.
I guess the assumption here is that writes are infrequent?
Yes, well, actually, I'll get to that a little bit. But yes, so LMDB only has one writer at a time, right? So only one writer can actually be accessing the database concurrently, unlike readers, which have no such limit. But actually, I'll talk a little bit more about the write scalability. Yeah, but that's a good point. Yeah, so the idea is that you've got these two different versions, right? And once those old transactions complete, those gray pages there can actually be reclaimed, right? And those will be used for later transactions. So that's how MVCC works in LMDB. So once you've kind of figured out what database you're going to use, you have to kind of decide what you're going to put in the database, right? If you look at the implementation of most SQL databases, they have like a record specification where you can kind of like a struct. You can say like this first field's an int and second field is a long or whatever, right? What I've chosen to use is this thing called flat buffers, right? Oh, and I should say that yeah, because people are sending JSON, I could just store JSON in the database, right? But then to extract just one field, if I needed it, if say I just wanted the kind out of a record, then I would have to decode the whole JSON, which would potentially be quite wasteful, right? So what I've chosen is flat buffers. It's this library that lets you encode things like pretty much the same as if you were writing like a C struct, right? You just lay out your fields, and to access one thing is just this offset into the struct and read it out, right? So in flat buffers, fields are not packed, right? Like if you use like protobuf or something like that, you would have to use like variable int decoding and so forth. Whereas here you just read them directly out. It's zero copy. If you have strings inside there, you can actually just get a pointer into the encoded data struct and use it directly without having to actually copy it. So that's what I just wanted to explain here a little bit with a little illustration. If you have a very regular application that was going to store a JSON in a file and then read it out and then use it, this is kind of what would happen, right? You have the disk, which stores like ultimately the data, and then that is read by the kernel into this page cache memory, and then your application would create a temporary buffer, call read, copy that from the page cache into the buffer, and then call JSON decode to break it up into something on, like, for example, on the heap, right? And that could be accessed, like fields accessed directly and so forth. One way to skip that, like skip one of those copies, is you could do a memory map, right? In that case, you could JSON decode directly from the page cache, right? That's what a memory map is kind of designed to do. However, if you take it one step further with flat buffers, this is what you do. You put that like previously expanded JSON decoded version, essentially, into the page cache, and then you access it directly via the mmap. So there actually is no copies, right? The mmap is not a perfect solution. There's all kinds of other potential overheads, but this is one cool aspect of it, and explaining how the LNDB works here, because you can be storing those flat buffers object inside the LNDB. So here's just a little example of a strfry relay that has created, I think imported 1 million events. And this is what the database actually looks like. And I'll explain what that means in a second. But LNDB has this thing called compaction, where you basically create the same database, but you reorder things, right? So they're a little bit more optimally. And I've actually annotated this here. So here you see that this is what, after 1 million events have been imported into strfry, what it looks like. You have the big block at the top called event. That's the flat buffers data, okay? And that will actually contain like the data that is useful for the execution of strfry to service the queries, right? So it'll have like the kinds and the pub keys and things like that that are needed for indexing, right? But the original JSON is actually stored in the event payload, right? And that's the idea, is that whenever I need to send a JSON out to the client, I could just take it into the event payload here, get a pointer into the memory map, and directly write that, right? If it's not, doesn't need decompression, it doesn't even need to necessarily hit the user space, right? Just gets written directly, in some cases, to the socket. And then you see there's a bunch of indices as well, right? You have to index to service filters. You have to index several queries, several fields in there, right? So I have a created index, and that's so that you can, if you want to traverse the events in order of when their created timestamps were and so forth. And you also have kind and a bunch of other indices there. Tag index is actually the biggest one, because people put lots of tags on events. And I just zoomed in a little bit here so you can see some other two indices. There's also a received at index and a replace index. Won't go into those in detail, but I did want to point out that, see how every section there has 2 different colors? That's my tool actually breaks it down so you see colors that represent the keys and the colors that represent the data, right? So if I go over and zoom in a little bit more into the ID index, you can actually see like this is mapping those IDs of the message, which are 64-byte hex, but 32 bytes hashes. It maps them to the IDs, the numeric IDs that I would store the event payloads in, right? So you can see that most of this index is the keys. Some of it is the values, and there's some space in between to make inserts better, like inserts more efficient. So as I said, one of the benefits of LNDB is that you can improve the query execution, right? You have a little bit more flexibility than a SQL database. One thing that is beneficial with strfry is being able to pause the queries, right? So if you have a really long-running query, you can kind of like pause it temporarily, and then a new query comes in, and you let it run for a little while, right? As opposed to using a SQL database, I have a lot more flexibility over the actual execution, right? So I don't want a really long-running query to be head-of-line blocking and preventing really fast queries from executing, right? So I have a kind of fairly primitive scheduling system there. One of the things that actually it's very beneficial for is if people send really complicated queries that match a ton of events as like a DDoS attack, which has happened before. We can kind of like put, we basically limit their outbound bandwidth, and then we have it so that if they hit their bandwidth limit, back pressure is applied, and we just pause their queries, right? So they don't really take any more extra resources. Oops. strfry itself is a multi-threaded and multi-process application, as I'll explain. But inside of one particular strfry process, there are these multiple threads that operate under a shared nothing message passing model, right? And the idea behind that is that every thread has like an inbox, and other threads create messages and push them onto that inbox, right? And then that thread wakes up, pulls off all its messages of inbox, and processes them. You may have also heard of this, like the actor model or something like this. There's also another like tiny asterisk here, in that threads indirectly communicate via the database as well, right? Because LNDB, is very, very easy to communicate between them, because it's mapped. The same thing is mapped in the address space, and they can easily just read out. LNDB is kind of like just a memory manager, right? It just is also a database, but You're just really allocating chunks in a memory, in a memory region. This is the architecture diagram of strfry, right? We have this WebSocket thread, which actually uses WebSockets and not CSOCs anymore. Sorry, Matt. But what it does is it accepts requests from the users and routes them to the ingester, right? The ingester ones, the ingester processes, I'll break it down in more detail in the next slides, but do a lot of CPU intensive processing of the message and then forward it either to the writer or to the request flow, right? And all these other threads will send messages back to the WebSocket if they want to reply to the user, right? So ingester, for example, would reply to the WebSocket if the message was malformed, right? It would say send an error back to the user. This is not a good message. And the WebSocket would do that, right? So as I said, WebSocket is primarily just a router. It multiplexes the connections using ePOL or KQ or whatever. There's only one WebSocket thread running. Except that, as I said, we can use multiple processes. I'll explain that more when we talk about reuse port. And that will actually let you to use multiple WebSocket threads if you want. Ingester does the CPU intensive work of getting the requests processed and routed to where they need to be. Some of the things it does are decoding the JSON. It validates the hashes and signatures of the request, which is actually the most CPU intensive part, is validating the signatures. And then it does some pre-compilation of the filters so that it's faster for the request thread to handle and so forth. And then after it's done, it routes it to the next thread in the pipeline, right? That's either the request flow or the writer flow or a couple other corner cases. The writer, as we talked about earlier, only has one thread running at a time as well, right? And the idea behind that is that LMDB actually itself only supports one thread of execution having a write transaction at a time, right? So yes, it's very important for your writes to be fast, right? They should not hold the write lock for very long, right? So usually what you try to do is do as much pre-processing as possible and then create the write transaction, immediately write your stuff, and then commit the transaction, right? And in most cases, for most workloads, it's sufficient to have just one thread doing that. But yes, sometimes that's a bottleneck in LMDB. So yeah, the idea is that typically the data will be read much more than written, and in this work case, in this workflow. So yeah, one of the nice things though is that we can actually amortize some of the transaction overhead by performing them in the same transaction, right? So as I said, the writer, like with all threads, has an inbox, and many messages can be pushed onto that. When it wakes up, it pulls off all those messages in the inbox, creates a transaction, and is going to write all of those together, right? And that amortizes the overhead so that you're not, for every message having to do an msync, right? Which actually will force it to be written to the database. This is actually a good counterbalance under heavy load because, the longer you're holding this write lock, the longer you're syncing and the more messages passing up, the more you'll amortize this overhead, right? So it works quite well. Another really cool feature about LMDB is this support for sub-transactions, right? And the idea behind that is that we create one write transaction and we have a whole bunch of operations we want to commit. Some of those could fail for various reasons, right? But you don't want to roll back all of the other ones that are unrelated to it. So each one we do, we create a sub-transaction that can be independently rolled back, right? Because those transactions might have been created by entirely separate users on different WebSocket connections, right? So sub-transactions are quite cool. Request worker is the threads that accept these filters, processes them by reading from the database, send the results back to the users, and then when they're done, send the connection over to the rec monitor, right? And that will be the one monitoring for future events. Rec worker, as I said, it has some scheduling of how it's actually going to process the database queries. So it will be able to pause the long-running queries and interrupt them and move the short-running queries in and so on. Yeah, as I said, when it's done that, it sends the end of stored events message, transfers the request over to the monitor. The monitor maintains this set of the rec subscriptions that are live, right? And will need to be sent the values of new events that come in, right? So anytime a new event comes in that matches the live filter, the rec monitor will detect that and send it to the WebSocket that's interested in it, right? And this is one of the ways that we sort of bypass the actor model threads, inbox threading system, and communicate via the database. The writer thread doesn't notify the rec monitor that a new event has come in, right? It just writes it to the database. And the rec monitor detects this with iNotify, right? That's the file system notification system on Linux. And there's similar things like Cake, you can do this as well. But it detects that, wakes up, and then processes all the events that since it last woke up and sees if any requests match, any filters match that, right? And the nice thing about the way rec monitor is built is that it's not just looping over all of the filters that have been installed. It kind of like breaks them up and creates like an inverted index so that it basically has a big list of all of the pub keys that would be all of the filters that are interested in a particular pub key, right? So if a pub key event comes in, it just jumps to that, and then it knows for every element in the list, those are the filters that are interested in it, right? That's another thing that strfry did to help the performance that other relays weren't really doing before. Another kind of cool feature is the live config changes, right? strfry has a config file like strfry.conf, like a lot of apps, and there's tons of parameters in there. Most of them you can actually just edit the file, change your value, and save it, and strfry will pick it up right away and start executing with those new values, right? So no restart required. It does this by, the way it works is that it also uses iNotify. If it detects a change in the config file, it will, read those new values in, and then atomically swap it with this config values pointer. And there's a little bit of a hack right now in that, like, once I swap it, other threads could still be listening to using that memory. So I actually just leaked that memory intentionally, right? Because it's a little bit too much overhead to use a shared pointer or something like this right now. And people don't change their config files that often, so I'm just living with it. Reuse port, very cool Linux kernel feature. I don't know if there's analogs on most other operating systems, but Linux is very useful. When you create a socket, you can pass this option reuse port. You know how you've probably launched a server before and it says, I can't listen to the port, something already is listening to that, right? If you use reuse port, that doesn't happen. You just listen, and multiple processes are listening on the same port at the same time, right? And the kernel load balances between them, right? So it'll like, first connection goes here, second connection goes here. First connection goes here, second connection goes here, and so forth, right? Which is quite useful for applications like strfry because you can run multiple independent instances, right? So for example, if the WebSocket thread ever gets overloaded, then you've kind of split it up so all of the different threads can handle all load balance between the requests, right? Another use case is what I call the zero downtime restarts, right? And the way that works is that suppose you do want to restart the server, like maybe you've changed a parameter that requires a restart, or you've upgrading the strfry binary, and you want to restart it without actually dropping any connections or having any service interruption for your users, right? The way you do it is you run another relay instance, and then you send this USR1 signal to the old instance. And that triggers what we call a graceful shutdown, right? And it tells that the old instance to stop listening for new connections, in other words, by closing its listening socket. And then it keeps processing all of the current connections until the last one exits, the last one closes, sorry, and then it exits itself. So that's a graceful shutdown. Nginx actually does something a little bit similar, but I don't think they use reuse port. They have like a file descriptor passing between instances or something, much more complicated. Yeah, as I said with the Nostr protocol, as I described the Nostr protocol, the relays don't actually communicate with each other, right? So clients are just purely responsible for posting their messages to many different relays, right? But strfry actually has this system called stream, where you can, if you want, set up a relay and pull down all of the events posted that to relay to yourself, right? It basically just acts as a client, puts in like a give me everything filter, and then gets all the events coming to it and writes it to its own database. You can also go the other direction, stream all your events that have been added up to the remote relay, right? So it creates kind of this like little mesh of relays potentially behind the scenes. So events get mirrored more reliably. Now I want to talk about negentropy, which is this other system I made that is in service of this mesh system, right? So the problem is that, as I said, in Nostr, clients post to many relays, right? They might decide for all kinds of reasons to post to a certain subset of relays or not, right? And sometimes relays stream events up and down to mirror them and so on. So these DBs often have a lot of overlapping events, but some might be missing certain events. It's quite chaotic often about whether you have full coverage, for example, right? So how do you officially figure out if you have all the events that another relay has, right? That's what negentropy is designed to solve. It implements a set reconciliation protocol, and the idea behind this is that because we're hashing the events, understanding that you have the same set of event hashes as the other side will determine that you have the exact same database of this selection of events, right? So one thing you could do is just send all of the IDs across to the other server, and it would just compare them against its big list of IDs. But that's quite bandwidth inefficient, especially if we're talking millions of events, right? So what strfry uses is a range-based set reconciliation. And the two sides basically compute this fingerprint of their event hashes, which is just the XOR of the hashes within a particular range, and alternate sending those XORs back and forth. So here is an example of like two servers that have pretty close to the exact same event set, except the left side is missing one at the bottom and the right side is missing one at the top, right? So the left side computes the XOR of all its events and sends it for the full range over to the right side. The right side computes its XOR, compares them, and sees that they're different, right? So something has to get done. So the right side then splits up its range into two chunks, into halves, and then computes the XORs of each one of those, sends them across to the other server. Again, both of those are different, right? So we know that we need to keep doing the protocol, right? So then the left side, again, splits up each of its received ranges into two ranges, sub-ranges, and computes the XORs of them, sends it across, right? And here's where the interesting bit happens, is that the right side now notices that some of those ranges are equivalent, right? They have the same XOR, the same fingerprint. So those ones don't need to be processed anymore, and it's just the differing ones that need to be changed, right? Or like need to be updated. So to continue the protocol, it splits again, recursively again, those sub-ranges into more sub-ranges, and computes the fingerprints, sends them across. Now, one thing you'll notice is that on the right side, one of those ranges was actually empty, right? And the base case value that you use for XOR is all zeros, so it would send across a 0 as the fingerprint for that. Once the left side receives that, it then knows that the other side has nothing in that range where I have something, right? So therefore, I have a value the other side needs, right? And it continues on, right? The other side, at that point, it then sends that value along with again, splitting up the range, right? And then, the right side, again, notices that, one of those values is 0, so the other side needs it, right? And then it simply sends it back, right? So we did that in 3 round trips, which, to correct these two elements, which doesn't really sound amazing, but that's how the protocol works as an illustration. In the real world, we're talking much more events, many more events, right? So if we got down to that level of events, I think it was like 12 on each side or something, you would just send the full list of IDs, right? It wouldn't make sense to do this at that low level, right? Yeah?
Sorry, why XORs again?
XOR is just a very efficient way to combine the hashes, right? And it's guaranteed that it will be unique given a set of events. Yeah, you could also use a different type of combination. Like you could actually compute a cryptographic hash, but it's much more expensive, right? strfry actually can compute the IDs using like 2 P XOR instructions, like the SIMD instructions. Extremely efficient way to combine, and it's equivalent properties about collisions and so on. Yeah. Right. So. As I said, if we get down to a small set, we're just going to send that list of IDs, right? And also, you saw that it was splitting it in 2s, right? Every range it would split in half. The negentropy protocol splits much more aggressively than that. Typically, it'll split up into 16 ranges. That's actually configurable, and you could make an implementation that does that dynamically depending on your bandwidth, right? So if you have very high bandwidth between two sides, you could split up into a higher range, set of ranges, right? So it's a trade-off between round trips and bandwidth consumed. Just a little bit of an analysis. Imagine that we have 1 million elements on each side, and their one element differs between them, right? Well, we know from algorithm analysis, if you're doing a binary search on 1 million elements, you need, log base 2 of 1 million operations, right? So about 20 operations. But however, let's say we're going to do what negentropy does, and we're going to split into 16 instead of binary search. We're like 16-array searching, hexarray searching. But in this case, we'll need about 5 operations, right? And then the other thing to notice is that if we're talking round trips, well, each round trip actually has 2 different splittings that can happen, right? So in fact, it would be about 2.5 2.5 round trips to compute, define this one element difference in a set of 1 million, right? So yeah, long and short of it is that syncing these 1 million element databases will take about 2 or 3 round trips, right? And if you actually look at the amount of bandwidth used, it's about 900 bytes in one direction, 600 bytes in the other direction, right? So it's quite an efficient protocol. And also the interesting thing is that a lot of those, a lot of these communications will happen in parallel. So yeah, you can fit more than 900 bytes in one Ethernet packet, right? Especially with compression or whatever. So yeah, you can actually be doing like multiple of these things at once without impacting the latency at all. If you do want to use negentropy for your own stuff, I've broken up into this little single header library. It's really easy to use. You just create the negentropy object and then add each item. strfry does a little bit more advanced than the reference implementation here, but this is all you really need to do, and this works fine into the millions of elements. You just add every item in your set, and then each one needs a timestamp for ordering, and it also needs the hash, which I called the ID here, because that's what it is on strfry in Nostr. And then when you're done adding your elements, you seal it, right? You finish it, you seal the envelope. And then you have two sides that have both done that. The client side, it really just creates this initial message, and then while the message is non-empty, it sends a query to the server, gets a response, and then it calls the reconcile method on the negentropy object, and you pass it 2 vectors, a have and a need. And as you're doing this operation, you'll discover new ones that you have and new ones that you have the other side needs, and ones that the other side needs that you have, right? And in parallel of doing this reconciliation, in other words, you can like glue together your reconcile messages with the actual missing messages. You can actually perform the reconciliation, right? And then eventually, you'll come up with a message size of 0, and you're done, right? Server side's even more simple. It just receives a message from the client, and calls reconcile itself for a response. Doesn't need to worry at all about the have or needs. This is all driven client side, so the server side can be stateless. And then respond to the client with the response. Yeah, so it's a fairly simple library to use. And all this is done to support what we call syncing. And the idea behind that is that it is pretty much the same as stream, but instead of sitting there and streaming events as they come in, you run it once and it syncs between the two databases. And I didn't actually put it here, but you can actually sync just a filter, right? So if you wanted to just sync the events created by one pub key, or sync the events created just in the last day or something like that, you could create a Nostr filter and just do the sync, right? And both sides would compute their filters of those 2 events and then do the negentropy protocol to reconcile. But yeah, if you have a mesh and they're all streaming events, usually the sets are going to be fully reconciled, right? So why do you need sync? Well, even in that perfect case, right? I said Nostr is very chaotic. Lots of stuff can happen, right? You could have one of the elements in your mesh go down for a little while, or a network connection could get disconnected, or a disk could fill up for an hour and not notice it. Like all these things have happened and more. Thanks. Or if you bring a new server into the mesh, right? You want it to be able to sync up. Another thing that we use this for is geo-replication, right? There's this cool project, relayable.org. They run strfry, and they run, I think it's actually even a couple more servers in this now, but a bunch of different servers in the mesh. And the idea behind that is that pretty much everywhere you are in the world, you'll have a fairly low latency connection to a Nostr relay, right? However, it'll be a globally, eventually consistent view of this database, right? So yeah, if you're in Australia, you can get a quite, relatively fast, like low latency connection to a Nostr relay, which is really important if you're talking like real-time apps, like a Twitter thing. You don't want it to be laggy. It's be bad user experience, right? And you can post there and everything will be fast and other users in Australia will see it right away. However, someone in like Brazil, for example, is going to take a little bit while for it to sync up, right? It'll either get streamed or fixed in a sync, but eventually it will be there, right? strfry also supports this thing called write policy plugins. And the idea behind that is that if you're running a relay, this is the internet, people are going to post all kinds of junk to you, right? Spam and objectionable things. So you need a way to like, to apply some sort of your policy filterings on them, right? The way that strfry does it is that it allows people to write some kind of filter program in any language they want. Any language that can read JSON from standard in and write JSON to standard out can be used to make a filter policy plugin, right? So the process gets the candidate event to see if it's acceptable, runs whatever logic on it, and then decides whether it wants to accept, reject, or shadow reject, right? Shadow reject is basically just pretend that you're accepting it, like tell them that they accepted it, but actually throw it out. Yeah. So it's quite flexible, and the community has made like many different plugins. Like, you know, surprising me, in fact, like things I never thought of at all. But you can do lots of really cool things. Some of the obvious ones are like rate limits based on IP or pub key, and like, you know, if someone is posting the same event, like spamming the same event content repeatedly, you probably want to start blocking them and so forth. And then there's also, you know, different moderation things you can do, like word lists to reject and prevent notes that tag like 1 million people. That creates like so-called hell threads. And yeah, someone's made a, you know, call out to ChatGPT to ask, is this thing spam? And you can also do people like this concept called paid relays, where, you know, if you subscribe to a particular relay network, you know, you'll be guaranteed to get good service, and also, you know, spam protection, because other people won't be posting. You know, the spammers won't have accounts there, basically. Really cool repo. Alex Gleason has a lot of other interesting plugins that have been made for it. Yeah, strfry also supports compression in various ways. One of them is the WebSocket message compression. And yeah, the WebSocket protocol supports compression in various ways. One of them is this sliding window, right? And if you consider how compression actually works, you know, one of the best things that it can do is reduce the redundancy, right? So if you have the same string repeated multiple times in a message, it will actually like kind of just have a back reference in the second one pointing to the previous one, right? So that's why, you know, things that have lots of redundancy compress well, right? WebSockets support this sliding window concept, where you can use all the previous messages that have been sent in this stream as kind of like things that you can refer back to when you're compressing a new message, right? And there's a bunch of other modes it runs in, but that's one of the things. And you use that with gzip. It's mandated in the WebSocket protocol. But there's this other really cool library called zstandard, and it supports this in a more like official way with what they call dictionary compression, right? You can do the exact same thing with zlib, like that's gzip and deflate, but zstandard basically does it better. Zstandard is pretty much better in every way, actually. So just as like a little bit of an aside here, one of the common criticisms of LMDB is that it doesn't compress multiple records together, right? So LevelDB, for example, is what they call log-structured merge tree. And when you commit a bunch of elements into the database, it will, you know, eventually like gather them up again, put them into a big block, and then compress that and write the compressed block out to memory, right? And you know, one of the nice things about that is that if you have two events, like two data records that have a lot of similarities, those similarities will get compressed, right? But you know, there's some disadvantages to that too, right? In other words, like if you want to pick out one of those elements, you have to decompress the whole block, right? And you don't want to be, you know, if you're going to look up many elements in this range, you don't want to be decompressing every time. So that means you have to have a cache version of the uncompressed data, right? Which basically means you're duplicating cache, right? You have the compressed version and the uncompressed version, right? Whereas, you know, LMDB doesn't have that problem. It's a single level store and no pre-decompression or anything like that, right? And also that's where some of the write amplification and LSMs come in, right? Is that you've written it once and then you have to read it again, compress it all and write it again, right? So you've doubled the amount of writes you need to, approximately. And then furthermore, like LSMs, you know, they're gonna arrange things by the order of their primary key, for instance, right? But who's to say that the primary key is the best indicator of whether or not these related events will compress well together, right? They just have, you know, they could have been submitted by entirely separate users at approximately the same time, right? And they're talking about totally different things, not even the same topics, right? So that's one thing you can use zstandard dictionaries for, or you could use zlib windows as well. But strfry uses zstandard dictionaries, and the idea is that you can take a whole bunch of events that you think are related in some way. Maybe they're posted by the same users, they have the same hashtags or whatever like this, and you can train these dictionaries, right? So you give them the events, and they'll strfry will use the zstandard library to create a dictionary that's called training, and it's basically like, you know, the most common strings that exist in this, more or less, right? There's some other things, but and the idea behind that is that you can choose, you know, no matter where they are stored in the database, you want this record to use this record to use this dictionary, and so on. You can pick the optimal dictionary for what that record is, right? The other cool thing is that like you can compute this offline, right? So you could sync down your data set, you know, run a job overnight to figure out the absolute best dictionaries for these things, and in the morning send up your dictionary to your servers and have them recompress based on this, right? So that's the kind of cool thing you can do. This is how you do it. Actually, there's this strfry dict command, and you run the training subcommand, give it a filter, for example, and that will actually run and create your dictionary, and then it'll give you a dictionary ID of 1, for example, and then you can say to compress this set of records, use dictionary 1, right? And there's also dict stats that'll give you like compression ratios and how many events are compressed with each dictionary and so forth. Another kind of interesting thing is, well, first of all, relay operators aren't going to want to give away all their secrets about spam fighting, right? Because that'll give away the keys, and the spammers will now know how to get around it, right? But here's like one kind of like interesting thing that you can do. You can actually use the dictionaries itself to figure out if events are similar. So one thing you can do is train your dictionary on like known spam or known objectionable content or whatever, and it'll create a dictionary with like bad words and other patterns like this that are potentially indicative that it's a spam, right? And then when an event comes in, you just try to compress it with these various spam dictionaries, and if it compresses really well, it's a good signal that it's spam, right? And of course, you probably want to use fairly small dictionaries for this so that you're not overfitting. Like you don't want like words like the to just end up in there and so on. So you definitely want to do some training of it. But that's another interesting thing you can do with dictionaries. Another little bit of another project that I wrote in service for strfry is Templar, and the idea behind it is it's an HTML templating system, and I'm sure all of us here probably have done this before, like create a template of HTML and you put in little fields and so on. But I think there's a really cool project called Hypertext CPP, and it actually has an even nicer syntax, like a better syntax than I've seen before for templating. And it requires actually parsing and understanding HTML. I'll show you an example in a second. But Hypertext CPP, I didn't really love that implementation so much. There's a lot of things I thought I'd improve. So, me being me, I thought it would be easiest to rewrite the whole thing. So some of the features I've added are automatic HTML escaping, so that if somebody puts in angle brackets in their username or something, there's no cross-site scripting attack, right? It also automatically minifies the white space in the HTML, and has some other features like JSX style grouping when you don't want to actually create an element and things like that. And templates can call it to other sub templates too. This is this is a simple example of the hypertext CPP format, right? So you see, it's just pretty much just like HTML, and that first little bit, the comments by $, open paren CTX username. This is kind of like a similar, a regular templating library, right? You just kind of insert your own little insertions into it, right? And that works the exact same way here, right? The interesting part though becomes when you want to actually do things like looping and conditionals and things like this. You can just pretty much tag them onto the side of a HTML element like this, right? And the great thing about this is it doesn't add another level of indentation, which is common in templates, and there's no end block and all this other things like that. It's just very clean. It's like reading HTML with some extra little features added onto the side of it, right? So this template, what it ends up compiling to is this C++ code, right? So it's a function called comments. That's just what we named the template. It's like the file name. And it takes this, templated type struct. And the reason I do that is just so I don't ever have to make a struct definition, right? You just sort of just use it like a struct and put in your values. This will work with any sort of struct that has username and comments attributes, right? So what the function does is it creates this string out, and then, appends all these little snippets of HTML from the template, and optionally appending, or in the places where it should insert, for example, the username, it calls append escape, right? And then if you go back to the previous one, you see how the comments have this little for loop modifier in there, the auto the reference to the C element in the comments vector is going to loop over that, and for each one append a div, right? And at the very end, it returns this Templar result. And the reason why it returns a Templar result and not a string is just that this Templar result can be inserted into other templates without needing escaping. Yeah. And yeah, the reason why I'm building this HTML library is because I'm working on this little site, oddbean.com. It's not live yet, but the idea is that it's pretty much Hacker News clone. If you've ever visited there, it probably looks familiar, right? But a lot of the Nostr clients are really like super heavy Web 2.0. Like you open your phone and it starts to get hot and takes like a minute to load like a 200 character message, right? I don't like that. I like fast, simple Web 1.0 websites, right? So that's why I'm building this. It basically uses the Nostr network as like the back end, but you have a nice, very simple, fast, even if you have a very low powered phone, for example, to browse it and so on. So yeah, this is rendered server side using those HTML templates, and you don't even really need JavaScript to browse this, right? If you want to post, you need a little bit of JavaScript, but yeah. So yeah, that's why I think Nostr is cool. It's just like any sort of interface you want to use to the network, you can, right? If you want a mobile app, you want a website, there's nothing stopping you from interacting with the network in any particular way, right? And you have your full data portability. If you change your profile on another site, you'll come here and you'll see your profile's all been updated, right? Everything is just compatible, chaotic, and a little chaotic, but also very community driven. And yeah, I just think that, the internet is a little bit too important to leave to like companies like Twitter and Reddit and so on. So I think something like this is where we should move towards. Yeah, and I think that's it. Thank you very much for listening. Here's the websites.